Okay, so now equipped with everything that we have learned so far about acceleration in special relativity and the equivalence principle that we have seen before, we are now ready to formulate the basic principles of general relativity. Okay, so this will be very akin to what Einstein did when he was trying to formulate special relativity, where you clearly first lay out the principles and then you develop the mathematics, which is to derive the Lorentz transformations based on those principles. Okay, so the principles were constancy of speed of light and and equivalence of the physical laws take the same form for all inertial observers. So now we'll do something similar for general relativity. We'll first lay out the principles, and then we'll develop the mathematics that that we can use to translate those principles into a language where we can do calculations. Okay. Okay, so about the principles of general relativity. So what we've seen so far is if you have an inertial observer, so this is like an observer in an elevator with two apples, right, where everything is just floating, staying where it is because there are no external forces acting on the system. And what we've seen is that you can make a coordinate transformation. This coordinate transformation can take you, for example, to an accelerated frame of reference. In this accelerated frame of references, these objects, okay, the inertial objects in that accelerated frame of reference. Now, remember the frame of reference is attached to the elevator. So as the elevator moves, the coordinates move. And in that accelerated frame of reference, these inertial objects, which are the apple, U, and this other apple, if you're in free fall, then it would seem to you in the elevator as if there's a gravitational field. Okay, that is, in the frame of the elevator there appears to be a fake gravitational field. So this is true if you have a uniformly accelerating frame of reference. Okay, now the analog of this in special relativity is the inertial observer is in a Minkowski inertial frame. Okay, where the transformations from one inertial frame to another inertial frame are not the Galilean transformations, but the Lorentz transformations. Okay, and the accelerated reference frame is just a change of coordinates, as we've seen, from x and t in one inertial frame to eta and rho in the Rentala frame, which is as close as you can get to a uniformly accelerated reference frame in special relativity. Okay, and now the claim is for the Rentala frame, in principle, this same equivalence principle tells you that there is no way to distinguish being in this uniform accelerated reference frame from being in a uniform gravitational field where you'll experience pseudo forces. Okay, so the Rentala observers will see the initial observers, as we discussed last time, as experiencing pseudo forces, except in special relativity, more strange things happen, like the existence of a Rentala horizon. Okay, and so this kind of gravitational field, this uniform gravitational field, is in some sense a fake gravitational field. Okay, it's not real in the sense that I can always make a change of coordinates. That is, I can always change my reference frame, and this gravitational field will disappear. Right? It just appears to be due to pseudo forces. Okay. However, what we would like to describe are what we call real gravitational fields, which are non-uniform. Okay, that is the key characteristic of gravitational fields. Is the non-uniformity distinguishes these fake gravitational fields from the real gravitational fields, which are non-uniform. Okay, and as we've discussed before, what is special about the non-uniform gravitational field, for example, if you now imagine these two apples and you in free fall in this non-uniform gravitational field where you're falling towards the center of the Earth, right? The gravitational field is non-uniform because the directions you fall are different. Okay, the direction of the gravitational field is different at different locations. In your freely falling reference frame, okay, what you would find is, yes, the apples stay exactly where they are, let's say roughly vertically relative to you. However, they appear to drift closer to you. Okay, so they experience what are called tidal forces, as we've discussed earlier. Okay, so what would have been initially parallel trajectories, if you're very far from the Earth, this is like vertically down. But what you find is if you wait long enough, these initially trajectories which look parallel, okay, actually start converging together. They start coming closer together. Okay, and this is really the hallmark of a true gravitational field, is that inertial observers, okay, as they're moving along their trajectories, initially parallel trajectories, they start moving, converging towards each other. Okay. So what we would like to do is to somehow describe these true gravitational fields, this true gravitational field in which inertial observers who are initially parallel to each other start converging towards each other. Okay, so the way we'll try to describe these true gravitational fields is as I mean, again, this is the hallmark of these true gravitational fields, is that inertial, that is freely falling observers, as we've already discussed, there's an equivalence between inertial observers and freely falling observers in a uniform gravitational field. These freely falling observers would start, even if they seem to be moving parallel, they would start coming closer together, okay, in a curved spacetime. Now, now locally, okay, if we just look at a small region of spacetime, in a small enough patch of spacetime, that spacetime looks, roughly speaking, like Minkowski spacetime. Okay, that is, if you're in a small enough region, you cannot tell the difference between that and Minkowski space. What you really have to do is look at another inertial observer and see, if I wait long enough, right, does that other inertial observer, does their trajectory appear to intersect mine? If it does, and if we thought we should have been moving parallelly, but now we see each other intersecting, okay, that's a signature that your spacetime is curved. Okay, so so inertial particles, okay, with no forces acting on them. Okay, so that is inertial particles with no forces acting on them. Okay, no forces meaning forces other than that of gravity. Okay, there's no force acting on them. Those particles, okay, the principle that we formulate is that they follow straight lines. Okay, and what do we mean by straight lines? Well, in Euclidean space, that is, if you imagine a sheet of paper, if I draw 2 points, right, the shortest path between these 2 points, right, I can draw many paths between these 2 points, but the shortest path is just the straight line that I can draw between them. So this is what we call a straight line. And what do we mean by a straight line? Well, a straight line is the one that minimizes the length of the path. Okay, this has a minimum path length between these 2 points. Okay, so in general, we won't require necessarily the criteria of minimum. Okay, it should extremize the path length. Okay, so what we'll say is that in a curved space-time, okay, so you imagine a curved space-time, and I'll tell you how to think about what we mean by a curved space-time. Inertial particles, okay, will follow paths that are will satisfy 2 conditions. One is that their paths will be time-like. Okay, that is, remember that the distance between 2 points in space-time is not a positive definite distance, right, or a positive semi-definite distance. This distance can be positive, it can be negative, and it can be 0. Okay, but the path it will follow will be time-like. Okay, which means in the metric signature that we are using, the distance will be negative. Okay, second, or the distance square will be negative, ds square. Okay, will be negative. And secondly, it will extremize the space-time interval along the path. Okay, so rather than being, so as we've seen, for example, in Minkowski space, right, you follow the longest path in space-time between these 2 points. Okay, if I want to get from some space-time point x1 to some other space-time point x2, okay, you will maximize the distance, the space-time interval between those two along the path. Okay, so this will sort of be the characteristic feature that we will look for in the general theory of relativity. One is that inertial particles will follow straight lines in this curved space-time. Okay, and the reason that you have curved space-time is the curved space-time is somehow describing these non-uniform gravitational fields. That is, the fact that parallel lines or parallel trajectories no longer appear to be parallel is a hallmark of curved spaces. Okay, and yeah, let me just show you a picture. Okay, where you can imagine this. So you imagine a sphere, okay, like this, and imagine, so now the sphere is not space-time, but rather it's space. Okay, but the analogy will somewhat work. So on this space, you can imagine, so let's say you're on the surface of the Earth, okay, and if you're near the equator, and you take 2 observers who are at the equator, okay, two people, imagine they're ants sitting on the equator, and they are trying to move in a way that is initially parallel to each other. So they will try to move this way. Okay, initially they will appear to be parallel. But what you will see is if they try to go on staying parallel to their previous trajectory, okay, eventually the straightest possible line they can travel is a longitude. Okay, so the straightest possible line they can travel is a longitude in this curved space. And so in this curved space, both the ants would eventually meet, okay, at the North Pole. Okay, and in fact, they would see that their trajectories are getting closer and closer to each other. Okay, so roughly the idea will be that that in a curved space, okay, initially parallel trajectories start converging. Okay, and what we want to do is generalize this idea to curved space-time and talk about initially parallel trajectories which start converging, and this will be a way to describe non-uniform gravitational fields. Okay, and the other claim is that a particle will travel a distance. So if I take 2 points on the sphere, it will the particles will travel the distance. Which path do particles take? Assuming that they start at A and end at B, which path do inertial particles take? Particles will take the path that extremizes the space-time distance. So if we think about a spatial distance between these 2 points, the shortest distance between any 2 points on the Earth is a great circle, right? You draw a great circle which has a center. Sorry, it has a center at the center of the Earth. Okay, so for example, longitudes are great circles. Okay, so you draw a circle like this. Okay, and this is, if given that I go from this point to this point, the shortest way to get from A to B is to fly along, is to go along this longitude. Okay, so for example, if you've ever seen a map of an international flight, right? Let's say to get from to get let's say from London to so if this is Europe, right, and this is London to the US, right? I mean, one way is you think the shortest way is like this, but on this curved space, okay, you actually have to fly along what is eventually a great circle. Okay, something that is a circle. Okay, the trajectory, if I continue, it would be a circle, and the center of that circle is at the center of the Earth. Okay, so these are called great circles, and the distance along this great circle, okay, between any 2 points is the minimum possible distance that you can travel. Okay, so the idea will be similar, except instead of doing this on a space, we will be doing this on a space-time where the distance measured can be positive, negative, or zero. Okay, the square of the distance measured can be positive, negative, or zero. Okay, one other point that will be important is that the laws of physics, just like in special relativity, we had a dictionary, right? And the dictionary was taking us from one inertial observer to another, and there was a particular kind of coordinate transformation associated with that, with those inertial observers, and the laws of physics had to be invariant or keep the same form under that kind of dictionary. Now, the law, we will demand a more general principle, which is that the laws of physics, okay, can be expressed in a way that preserves their form not just under Lorentz transformations, but under any kind of coordinate transformation, linear or nonlinear, a general coordinate transformation. So it doesn't have to be a linear transformation, doesn't have to be just a Lorentz transformation. Any general coordinate transformation, the laws of physics will preserve the same form. Okay, this is not true in special relativity, right? But as we've seen, okay, for example, if you inertial observers versus accelerated, uniformly accelerated reference frames, that is going from, the xt coordinates to the eta rho coordinates, right? It's really, you're just describing the same physics in just different coordinate choices, okay, that uniformly accelerated frame. So, so there must be a way to describe it in a way that is coordinate invariant, okay, or coordinate covariant, which changes in a specified way, but the equations take the same form in all coordinate systems. Okay, so this principle of general of transformation under general coordinate transformations is also called general covariance. Okay, this principle is called general covariance, and okay, so now roughly, okay, what we started when we said we want a merger of special relativity plus the laws of gravity. Okay, what we were looking for was two things. One is we were looking for a generalization of Newton's laws. Okay, that is, if we think about Newton's laws, let's say in the absence of any forces, okay, we saw that this is the law. Okay, Now, equivalently, we could have thought of this as coming from a particular action. Okay, and that action is basically a measure of the path length between two space-time points A and B. Okay, and the path is the one which extremizes that action or extremizes the distance between two space-time points. So, so this action basically you can use it to derive these equations of motion, and this equation of motion is basically Newton's law. Okay, for particles with no forces acting on them. Okay, so what we will see is that instead of having a path through flat space or flat space time, which is Minkowski space time, what we will see is that there is a way to talk about a curved space time. Okay, and in that curved space time, the path between any 2 points on that curved space time now will be an extremum. Okay, and so we will either find the shortest, longest, or maybe a saddle point path through this curved space-time, and so either you will maximize or minimize this action, okay, in getting from point A to point B. Okay, so the only difference is that the metric, right, which is the measure of distance on these curved spaces, as we will see, is coordinate dependent. Okay, so it's no longer just -1, 1, 1, 1. Okay, it's actually coordinate dependent in a curved space-time. Okay, but just being coordinate dependent is not a guarantee of curved space-time. Okay, so in a curved space-time, g mu nu of x, okay, can be will be coordinate dependent, and in fact, there's no one coordinate system which I can go to where I remove the entire coordinate dependence in g mu nu of x. Okay, in the metric. Okay, and so the first thing we were looking for is an analog of Newton's laws, and basically that analog of Newton's laws will come from the statement that point particles travel a distance which extremizes their path through space-time, and so that will give us an action, and if we take the equations of motion corresponding to that action, that will give us the analog of Newton's laws. Okay, so we'll follow this procedure to get the equations of motion. The second thing that we wanted when we wanted a merger of STR and gravity was we wanted an analog of Poisson's equation, right? We wanted some analog of this, okay? And the analog of this is called Einstein's equations, okay? And roughly the statement will be, so we saw that the right-hand side, some appropriate generalization might be to think of this as a stress energy tensor. Okay, the question was, what do we do about the left-hand side of this? Okay, and the answer will turn out to be that the curvature of space-time, okay, that is how much space-time bends, okay, is going to be the left-hand side of this equation. And roughly speaking, the left-hand side of this equation will involve second derivatives of the metric g. And since the metric g depends on your space-time coordinates, these derivatives are non-zero. Okay. And also it will be non-linear. Okay, so it'll have some powers of g. Okay, it'll be some complicated non-linear functional of the metric g. Okay, so schematically, this is what the equation looks like. It looks like some second derivative non-linear equation in g is equal to t mu nu. Okay, so this tells you something about the curvature. Okay, so in fact, you have to solve this equation for g, which is like solving, roughly speaking, it's like solving for the gravitational potential in Newtonian mechanics. And the difference is that here you think about gravity not as a potential, but as a curvature, as some kind of measure of space-time distance between space-time points. And in particular, you're solving for this kind of curvature. Okay. And so the point is that this metric distance, the distance between two space-time points, is not a fixed quantity, okay, when you think about it in general relativity. Rather, you think about it as dynamical, okay? That is, it's determined by the kind of matter and energy distribution that you have that sources the curvature of space-time, okay? So this is captured by this slogan, okay, that basically the geodesic equation, or the fact that particles travel the shortest distance to space-time, is given by the statement that space-time tells matter how to move. Okay, that is, in a curved space-time, particles will follow the shortest the extremum distance between two space-time points. And this equation tells us that if you have matter, okay, any kind of matter or energy, then this matter or energy will cause the bending of space-time. Okay, so matter tells space-time how to bend. Okay, so essentially the essence of GR is just captured in this one statement. Okay, the bending of space-time in a bent space-time or a curved space-time, okay, that determines how matter will move. Point particles will follow geodesics, or shortest paths or longest paths in that space-time. And conversely, matter or energy determines the curvature of space-time. Okay, and matter will tell space-time how to bend. Okay, so we will try to put these statements more mathematically rigorously, and then also hopefully it will become clearer what these ideas mean. Okay, rather than talking about in terms of these cartoon pictures. So as I mentioned earlier, there's one big difference between curved space and curved space-time, which is that the distance, or the distance square measure in space-time, is not positive definite or semi-positive definite. That is, the distance between any 2 points, okay, can be positive, it can be 0, or it can be negative. Okay, it doesn't have to be. So the distance between any 2 points in Euclidean space is always positive. Okay, in space-time, in a curved space-time, it can be positive, 0, or negative, just like in Minkowski space. Okay, and just like on a curved space, you can always draw coordinates which locally seem flat. Okay, like you can draw approximately, right? If you're on the surface of the Earth, you would think that the Earth is flat. I mean, people thought this for thousands of years, right? And it's only when you start traveling, long distances, or you can see some effect of what happens at longer distances, that you realize that the Earth is curved. Okay, so so similarly, the idea is that in a curved space-time, locally your space-time looks like Minkowski space-time, but globally, like if I look at if I go to one patch of space-time to another patch of space-time, okay, then I see that my space-time is made up of many patches which are locally flat, but when I patch them together, I see that my entire space-time is curved. Okay, so just like patching these together on the surface of a sphere, roughly these look like flat patches, but when I put them on the sphere, then I see that the space-time is curved. Okay, so that's going to be the rough idea. And how do you detect this curvature? Well, as we've discussed before, curvature is detected by inertial observers. Inertial observers are the freely falling observers. The freely falling observers are the ones that follow geodesics, or the ones which maximize their space-time interval that they travel between two space-time points. Okay, and the fact that these geodesics, which initially start out parallel, no longer remain parallel, okay, that is, they start to converge, that is the hallmark of a curved space-time or a non-uniform gravitational field. Okay, so the fact that you see this non-uniform gravitational field, or equivalently tidal forces, that is, it's like those two apples which are falling, right? Those two apples appear to get closer together. Okay, so the fact that you see these tidal forces is kind of like the signature of this non-uniform gravitational field. Okay, so let me just summarize what I just said today. So if we want to lay out these equations of general relativity, okay, and roughly these are two equations. One is the geodesic equation, which is an analog of Newton's laws, okay, which is really the statement of traveling the shortest or longest distance in space-time. The second equation that we have is Einstein's equations, which is the generalization of Poisson's law. Okay, and this will tell us that the curvature of space-time is related to the matter or energy density in the universe. And if we want to understand these equations of general relativity, we first need to develop the mathematics, okay, that is needed to describe curved spaces and curved space-times. Okay, and the mathematical framework is not something that you have studied before for most of you. Okay, and that framework is called differential geometry. Okay, so we'll first have to develop the mathematical framework of curved spaces or curved spacetimes, and that mathematics is described by something called differential geometry. Okay, so for the next few weeks, what we will do is we will spend some time developing our understanding of the mathematical ideas. Okay, and this is where actually there's a big difference between special relativity and general relativity. The mathematics of special relativity is relatively simple, right? It's just algebra, okay, to get the Lorentz transformations. In general relativity, it's more, there's geometry, and then there's calculus on curved spacetimes. Okay, so we will want to try to develop those ideas of how to do mathematics in curved spacetime. Okay, and that is basically going to be the focus of the next few weeks. Okay, so I'll pause here for any questions. Yeah, Utkarsh.
Yeah, can you go back to the Poisson equations equivalent formula?
Here.
Yeah, the
This,
current one. Yeah, this one. So, couple of questions. First of all, we see that there it is 8 pi g, whereas for Poisson equation it's 4 pi. So there's a change of factor of 2.
well, I could have always defined this as 4 pi g, and then I could absorb this factor of 2 into, I mean, we don't really know the mapping between this g and this phi yet, right?
Yeah. Okay. And
So
g is right.
this g is the same g though. Yeah, this g is the, sorry, the capital G is the same g Newton. This small g is the metric.
Okay.
Okay, as I told you, in one of the introductory classes, right? We don't quite know when we generalize phi what we want to generalize it to,
Yeah. Yeah.
right? It'll turn out to be this kind of tensor, but even the way we talk about tensors will be very different in a curved space-time. So we'll have to develop that machinery as well.
Okay. And it's an raised to an arbitrary power, right? And
It's not exactly this. It's actually going to be some nonlinear. So G, you can think of it as a matrix. So it'll involve things like derivatives of it'll involve things like G inverse, okay, partial G's, things like this.
okay. Okay.
Okay, so it'll be more complicated than, yeah. Yeah, Malvika.
Yes, so I in this equation itself, I sort of mathematically get how the left hand side is sort of the curvature, but how do you physically understand at this point? I mean, how matter and energy are the sources of curvature of space time? Like, I mean, historically,
Oh,
how would someone understand that?
no, historically, the idea is really coming to this non-uniform gravitational fields, right? So the fact that, so the physical points are that you have inertial observers, okay? And inertial observers in Minkowski spacetime, like those, if you imagine those two apples, right? They will just stay here, okay? And now if I go to sort of an accelerated frame of reference, then in that accelerated frame of reference, they would both appear to fall, but they would always remain parallel to each other in the accelerated frame of reference, right? So now basically the idea is that if you have a non-uniform gravitational field, in a non-uniform gravitational field, the expectation is that the apples should move towards each other. Okay, so this equivalence principle holds for the uniform gravitational fields. So the question is, what happens in a non-uniform gravitational field? Okay, and so therefore the idea is that if I look at a small enough patch of Minkowski's of space-time, then locally it should look Minkowski in that these apples appear to fall parallelly to each other. Okay, but the fact that these apples don't fall parallelly to each other and that they in something like this in a non-uniform gravitational field, the fact that they move towards each other, okay, is a hint that your space-time is not flat, okay, or it's not Minkowski. Okay, really, again, with analogy with curved space, right? If I draw flat space, if I draw two parallel lines, they will continue to remain parallel forever. In a curved space, initially parallel lines converge. Okay, so the idea is really essentially just like that, which is instead of having a Minkowski or what we'll see that this is the correct generalization of flat space to flat space time. We will actually go towards and again you can think of the sphere as locally small patches which are flat, but as I patch them together I see that my entire space is curved. So essentially it's going to be the same idea, which is locally you will have Minkowski spacetime, but as I patch together pieces of spacetime, that is literally I think about x and t, take a small region of x and t, this is a patch of spacetime. But as I patch together different regions of spacetime together, I will see that I have a curved spacetime overall. Okay, and that would explain why these apples in a non-uniform gravitational field don't start converging together. Okay, and basically we want to describe these non-uniform gravitational fields because the uniform gravitational fields we've seen are fake, right? They're just the artifact of they're just an artifact of your coordinate system. Okay, but the non-uniform gravitational fields are real in the sense that you experience a physical effect, which is these tidal forces. Okay, and so this non-uniformity of gravitational fields is described by curved spacetime. Okay, that's the physical idea. And the curvature of space-time is sourced by whatever is causing the gravity, which is in this case the Earth. Okay, so this equation, right, is really like Einstein's equation, is really like Poisson's equation in the sense that the curvature of spacetime is being sourced by some matter or energy, okay, which is the generalization of Poisson's equation. Except instead of sourcing just a potential, you source curvature of spacetime.
Okay, sir. Thank you.
Did that make sense? Or I mean, I hope the physical idea is coming across.
Yes, so it does make sense because gravity comes from masses, and here we are connecting gravity and space-time, so it does make sense.
Hello.
Yeah.
Hello. Sir, am I audible?
Yeah. Yeah, I can hear.
Sir, the equation where you have written, can you show the equation? Einstein.
Yeah, here, this one.
Yes, sir. On the left hand side, can you think of it as a, I mean, taking 2 times gradient is like doing p square over, and applying a kind of operator on the field associated with the gravity. I mean, can you think of it like this? Like p square by 2m, and then right hand side it is all energy. I mean, instead of thinking G as a space-time, can you think of it as a field?
Yeah, that's perfectly fine if you want to think of it as a field, except again, this is non-linear. Okay, so I mean, this is not really like, you know, I mean, if you're trying to draw an analogy with Schrodinger's equation, I mean, first of all, these derivatives also appear in different combinations. Okay, so it's not that it's just going to be partial x square plus partial y square plus partial z square.
I mean, kind of analogy can.
I mean, it's a second order differential equation. So that much is true. It's a second order non-linear differential equation.
Okay, sir.
Okay, but again, even this is sort of the fact that it's second order non-linear is the second order is only because we demand lowest order in derivatives. Okay, what is the lowest order in derivatives which is consistent to describe this physics? Okay, it turns out to be second order. Okay, more questions?
Sir, here, I mean, I'm just trying to sort of understand it. So clearly the metric that we are talking about is not a metric in the mathematical sense because it's not positive, definite, etc.
No, it is in the mathematical sense. You have to generalize your mathematical notion of what a metric is. Just like we have Minkowski metric, which is not positive definite, right? It's it's really a measure of distance in space-time. It's the only measure that all inertial observers agree on.
Right. So would it be right to say that it's basically the local Minkowski metric in the curved spacetime sort of? Or like
okay,
I mean,
so let me say this. So G mu nu locally, okay, even in a curved spacetime, roughly speaking, you can think of it as if I'm in a curved space-time and I go to a small enough patch. In that small enough patch, I can always find a coordinate system in which my metric is flat, right? So locally, it is always possible to go from a coordinate-dependent G mu nu in a small region of space-time to, or at a point, to a coordinate system where you'll just get eta mu nu. But it's not possible to make this change of coordinates such that this change of G mu nu to eta mu nu happens everywhere simultaneously. Okay, that is basically why the spacetime is curved.
yes, that makes sense.
Okay, any more questions? Okay, all right, so let me just explain what the plan is, okay? So it's going to get very mathematical for a little bit, okay? And then we'll come back to the physics, okay? So the mathematics that we're going to try to set up is the mathematics that is needed to describe curved spacetimes. Okay, so how do we describe curved spacetimes? How do you describe shortest paths in curved spacetimes? Okay, shortest paths in curved spacetimes. How do we set up all of this? That is the mathematics that we're going to set up. Okay, and shortest path in curved spacetime. So we're going to try to set up all this mathematics. Okay, so a lot of it will involve definitions, and the other thing is, you know, when we take shortest path, right, you're trying to minimize, you know, infinitesimal distances. So what this means is essentially that you'll have to develop some kind of calculus, okay, some notion of how to take differentials, okay, on a curved spacetime. So we'll have to develop all this mathematics, okay, and we're going to spend some time first developing the mathematics. It will take a few weeks, okay. I mean, in fact, you could take a full course on this, but we'll develop the essential parts, okay. And once we have these essential parts, and once you understand the basic ideas of what is needed to describe a curved spacetime, then we will return to trying to actually get these equations, okay. We'll try to get the action for a point particle in a curved spacetime, and the analog of Newton's law in the absence of forces, or even in the presence of forces. And then we'll try to get the analog of Poisson's equation, okay, which is where we'll try to get these Einstein equations, where we get something like curvature is equal to some T mu nu, okay. And you see that basically these laws, or this idea of curved spacetime, naturally has the equivalence principle built into it. Okay. Okay, so today what we're going to do is we are going to get started with describing curved spacetimes. Okay, and in general, the mathematical notion of spaces, okay, any kind of space, whether it's a space or a spacetime, is this idea of something called manifolds. Okay, and so today what we're going to do is we're going to talk about, we're going to try to get to manifolds, okay, but we will probably get to it only next week. Before that, what I'm going to do is, so mathematicians like to talk sort of in different increasing levels of abstraction. Okay, and so let me try to tell you about some of these levels of abstraction when you try to think about space, any kind of space. Okay, so the highest level of abstraction is this idea of what is called a topological space. Okay, and topological space, let me just give you a rough idea of what a topological space is. So topological space roughly will mean a collection of points with some idea of what is a neighborhood between points, okay, or what points are in the neighborhood of some other point. Okay, so roughly topological spaces deal with points plus neighborhoods of points. Okay, this seems like it shouldn't really tell you much about anything. Okay, but surprisingly, just the idea of points and neighborhoods of points contains a lot of information about spaces. And as we'll see that, you know, so there's some characteristics of spaces which only have to do with the topological properties. That is about what are the points in the space and what are the neighborhoods of those points. Okay, and there are a lot of properties which just follow from these simple ideas. Now, manifolds are a little more complicated. So now when we talk about this kind of spaces, we are going to try to do calculus on these spaces. Okay, and when we try to do calculus on these spaces, there are particular types of spaces that we'll consider, and those spaces are manifolds, okay, on which you can do this kind of calculus, and we'll develop the calculus that you want to do. Okay, because in physics you have to do things in terms of like differentials, like what happens if the position changes, what is the rate of change of position, and so on. Okay, that's what I mean by doing calculus. Okay, or calculating an integral, which is the action, right, which is what is the total path that I travel from here from A to B, given that I know infinitesimal paths. Okay, so how to do integration, differentiation, okay, on a space. Okay, that when I introduce that extra idea onto these topological spaces, then I get a manifold. So manifolds are a subset of topological spaces on which you can do this calculus. Okay, and a third thing that we'll talk about is all these spaces that we talk about actually don't necessarily have a metric on them. Okay, so these manifolds don't necessarily have a measure of distance between any 2 points. Okay, you can think about a choice of a distance measure, but you don't have to. Okay, once you impose a choice of a distance measure, that is, once you impose a metric, okay, which allows you to measure distances between any 2 points on the manifold, then it becomes a metric space. Okay, so what we will do is in decreasing levels of abstraction, we'll start with the ideas of topological spaces. This is not something that's usually covered in GR textbooks, but I think it's good for you to know this. Then we will move towards the idea of manifolds, and manifolds will be the most important thing because as we've seen in this basic idea of developing GR, we will have a curved space-time, but the curvature comes from the metric, okay? And we have to solve for the metric. The metric is one of the equations which appears in one of the equations that we're solving, okay, which is Einstein's equations. And we want to solve for G min U. So a priori, what is the object that we are working with before we have a metric on it? That object is a manifold. Okay, so you can talk about a manifold where the metric is not yet fixed. Okay, the measure of space-time distance is not yet fixed. And on that manifold, you're trying to find out what the metric is. And to set up those equations, you know, the second derivatives of the metric and so on, what you mean by all of this, the first thing you have to do is somehow define calculus on this space. Okay, so that we'll do, and that will lead us to the concept of manifolds. And finally, we'll talk about metric spaces and spaces with a distance measure between them, and you know, various things that you can do on metric spaces. Okay, so today's plan is today and tomorrow probably we'll talk about topological spaces. Okay, and then we'll get to this idea of manifolds. Okay, so this discussion on topological spaces, like I said, most GR textbooks don't deal with this. So it's there in the appendix of Wald. It's not there in Sean Carroll. Okay, so Wald's book has it in Appendix A, but in more detail, and this is where the discussion that I'm going to follow today is based on. There's the book I told you about by Nakahara on geometry, topology, and physics. Chapter 2 of that, okay, I'm following that discussion on topological spaces. Okay. Okay, so let's start with the definition of a topological space. Okay, so what do we mean by a topology? And the definition is actually quite simple, but let's try to understand it carefully. Okay, so the definition is that first you have a set. Okay, that set is X. Okay, and you have two ingredients. One is you have the set, and the second thing that you have is a collection, which we'll call T, of subsets of X. Okay, so T is also it's a set of subsets. Okay, so T is a set of subsets. With each subset I'll denote as UI, where I belongs to some. I mean, this is a label for these subsets of X. Okay, and these UI are subsets of X. Okay, now it could be any number of subsets of X. Okay, but this number of subsets of X, so this X plus its subsets which are encoded in T, these must satisfy three properties. Okay, so let's lay out those three properties. So the first thing is that the null set and the set X, okay, which are subsets of X, both of them belong to T. Okay, that is the first condition. That's a simple enough condition. The second condition is supposing I take some other list J, like I had this capital I, which was a list of subsets. Suppose I take some other list J. And it may be infinite, okay, and it's some subcollection of the subsets of I, subsets which are denoted as I here, which make up T. Okay, so if I take some subcollection of I, then the family Uj, okay, where I take the subsets which belong to this subcollection J. Okay, so J is, let's say you can think of it as a subset of T, where T itself is a set of subsets of X. Okay, so I take this J, okay, and for any collection, so this J is a collection of subsets. I take the union of all those subsets, and even the union of all those subsets should belong to T. Okay, that is a condition that you demand on T. Okay, so T, so let's think about X. So this is X. I take any number of subsets of this. So if I think of a Venn diagram, this is one subset U1, this is another subset U2, this is another subset U3. These are potentially overlapping subsets. And now I have some list of sets. Okay, and so there's U1, U2, U3. Okay, I have some particular list, and that particular list is what I call T. Okay, and now the claim is if I take a subset of these, so suppose I just take U1 and U2, okay, and let me call this J. Okay, or sorry, let me just think of this as, I mean, there's a subtlety, but I think of this as labeled by belonging, the subscript belongs to some set J. And now the claim is that even the union of U1 and U2, that should belong to T. Okay, so T should also contain things like the union of U1 and U2. Okay, the next thing is, now if I take any, and this is true even if I take an infinite number of sets, okay, in J. Now the last condition, so these are two conditions, phi x belong to T, and any subcollection of these subsets, okay, the union of those should also belong to T. Okay, and the third condition is that if I have any collection K, okay, of I, again, any subcollection, but this time all necessarily finite, okay, then the family, which is UK, which now belongs to K, okay, so just like I chose U1, U2, which belong to some J, I choose some U3, U4, which belong to some set K, okay, and the intersection now of U3 and U4 must also belong to T. Sorry. Okay, and this should be true for any collection K. Okay, so the key difference between these two conditions is that in this condition you're allowing maybe an infinite collection, okay, of these subsets. Okay, so I can have an infinite collection. So imagine I'm making them smaller and smaller, and I collect all of them. Their union should also belong to T. Okay, it should belong to this set, collection of subsets. But when I take the intersection, the set of sets or the set of subsets that I'm considering is always finite. Okay, so I don't take an infinite collection of these. I only take a finite number of these. Okay, I pick them out from T. I take a finite collection of them, take their intersection, and the intersection must belong to T. Okay, so these conditions seem very simple. Okay, that's all. So this defines a topological space. I need a set X. I need a collection of its subsets T. Okay, and now this set and its collection of subsets must satisfy some criteria. Okay, the criteria is, one is phi, the null set, and X belong to T. The second criteria is if I take a subcollection of those subsets, okay, then the family of those subsets, if I take their union, that should also belong to T. Okay, for any arbitrary subcollection, including an infinite subcollection. Second, if I take any subcollection and but as long as it's finite, only, okay, it only has a finite number of subsets in it, then the intersection of all of those subsets should also belong to T. Okay, that's all. Okay, very simple conditions that describe what you mean by a topology or a topological space. So you say that X and T together form a topological space. Okay, or sometimes you say X forms a topological space and T gives it its topology. Okay. Okay, so let's do some examples, okay, because this seems very abstract, but surprisingly, just these simple definitions will lead to very rich properties, okay, of topological spaces. Okay, so any question about these definitions here? Okay, maybe we'll do some examples and then you can ask your questions. Okay, so the set, so just some nomenclature. Okay, the UIs which belong to T, by definition, are called open sets. Okay, it's just a name. Okay, we're giving it the name open sets. The sets which belong to T are called open sets. Okay, and we also say, as I told you earlier, that T is said to give a topology to X. So X is a space, which is a collection, it's a set, and T is a collection of its subsets. And T, if X and T together satisfy those properties, then T is said to give a topology to X. Okay, so let's do an example. Okay, so one example is, if I take T to be all the subsets of X, so I have some space X, and now T is all the subsets of X. Okay, so we can check that all these properties are satisfied. Phi X belongs to T. Okay, then this property is also satisfied, because if I take any subcollection, okay, of subsets, if I take their union, then the union also belongs to T, because T contains all subsets, okay, of X. Then if I take the intersection, okay, of any subsets of T, then that will also belong to T, because T contains all the subsets. Okay, so this is called a discrete topology. Okay, and we'll see why it's called a discrete topology in a moment. Okay, but this is what we call a discrete topology. Then another topology that you can have is X is a space, is a set, and T only contains two subsets. It contains phi, the null set, and it contains X. Okay, this is necessary by the first condition. Okay, it should contain phi and it should contain X. Okay, and this is called a trivial topology. Okay, so let's see if it satisfies the other two conditions. So so let's take a subcollection of the sets in T. Okay, so for example, we could take just phi. Okay, and sorry, let's just take X. Okay, so if we take X, we see that the union of X with itself, okay, is T, is in T. Okay, and similarly, the intersection of X with itself is X, and that also belongs to T. Okay, and you can do this with phi and X as well. You just have to keep some subtleties in mind about phi union X is X. Okay, and phi intersection X is phi. Okay, so if you keep these subtleties in mind, then you can see that even this topology is satisfied. So for any X and T, you can always define, for any set X, okay, it's always possible to define a discrete topology, which is you just take all the subsets of X. Okay, that's not so interesting. Okay, I mean, it's interesting, but it's less interesting. Okay, it gives you the discrete topology. And another less interesting case is this trivial topology, where you just take two subsets in T, that is, you take phi and X. Okay, this gives you the so-called trivial topology. Okay, but now let's come to some more interesting examples. Okay, so let's take X to be the set of real numbers, okay, or the real line. Okay, so X is the set of real numbers. And now let's take T to be the set of all open intervals. Okay, open intervals in the sense of real numbers. Okay, so I take open intervals A, B on the real line. Okay, plus I also take the union of these open sets. So for example, if I have a set between 0 and 1, okay, and a set between 3 and 4, okay, I take the union of these two, okay, as also being a member of T. Okay, and arbitrary number of unions of these open sets I take to be as members of T. Okay, now you would say, if I do this, well, what am I excluding, right? It doesn't T contain all the subsets of X? Okay, now sorry, and one more point is that this A, B, I can take them to be infinity also in a proper limiting procedure. I'll assume that these open intervals can be extended to plus minus infinity. Okay, so let me ask a question. Can you already look at this and tell me what I am excluding from T? What subsets of X are not included in T? If you have the notes, you probably already know the answer, but let me just ask.
Things like closed intervals or intervals which are closed on one side.
Yeah, good. So what is not included in T is closed sets, closed intervals. Okay, and in particular, discrete points are not included. Okay, for example, so on this rail line, for example, supposing I take, let's say 0, 1, but I take the closed interval, so include 0 and 1 in this interval. Okay, then what you see is that even if I take a union of any number of open intervals, either they will consist of disconnected open intervals, okay, or they will combine, like if they're overlapping. For example, if I take 0, 1 union half 3 half, okay, the union of this will be the open interval 0, 3 halves, which will still be an open interval. Okay, it will never include these kind of closed intervals, so it will never include something which includes these boundary points as well. Okay, so those are the subsets that we're excluding from T. We're excluding these kind of closed intervals, or even, you know, something like this. Okay, left close, right open. Okay, or left open, right close. Or the specific limiting case of something like this is where you just have a single point, okay, in a closed interval, which is just that point itself. Okay, so a single point like 1 by itself is not included inside T. Okay, so T doesn't include discrete points or these partially closed or fully closed sets. Okay, so this gives you a topology which is not just the discrete topology. It doesn't include all the subsets of X. Okay, and this topology is called the usual topology. Okay, this is going to be the most important topology for us. Okay, and this topology can now be used to define a topology on a space X is equal to Rn, okay, the n-dimensional space. Okay, so if I have n-dimensional space, so first of all, when I have two sets A, B, okay, I can define a set A cross B whose elements are ordered pairs, okay, of AB, okay, where A belongs to A and B belongs to B. Okay, so this is a definition of a cross product of sets. Okay, so Rn you can think of as R cross R cross R n times. Okay. Okay, so now what we can do is on Rn, okay, we can define a topology by defining T to be things like open intervals on each of these rail lines. Okay, and we take their cross product. Okay, so this is an open set cross another open set cross another open set. So we take all of this, okay, and we take unions of all such of all such open intervals, okay, or cross products of open intervals. And so just the way you define the usual topology on the rail line, you can now extend this definition of the usual topology to include the space Rn. Okay, and let's check that this topology is actually a topology. That is, let's check that it satisfies the conditions that we outlined above. So suppose we take okay, so let's just do it for this case. Okay, let me just make some space here. Okay, so on the rail line, okay, we've taken T to be sets of all open intervals and their unions. Okay, so now supposing we take any arbitrary subcollection, okay, of T. Okay, so that is, we take, let's say 3, 4 and 1, 2. Okay, and let's say we take this subcollection. Okay, and we take their union. The union of these automatically belongs to T because we've already by definition inside T included the union of all these open sets. Okay, this is true even if we take an infinite number of these. P4, okay, sorry, let's say 2, 3. Sorry, not 2, 3. So let's say 1, 3, 2, 4, okay, 3, 5, and so on. So if we take the union of all of these and you have an infinite number of them, okay, then you will get something like 1 comma infinity. Okay, and this will also belong to T. Okay, because as we said, you can extend A and B all the way up to plus minus infinity. Okay, so the union of any arbitrary number of open sets, okay, or things belonging to T also belongs to T. Okay, so this satisfies the second criteria. The first criteria is obviously satisfied, right? Null set belongs to T. Okay, I take the interval which is vanishing interval. Okay, so or by definition, let me just include phi. Okay, inside T, and I can also take the whole of X. Okay, the whole of X is the rail line, which is basically the open interval minus infinity to infinity, and that belongs to T as well. Okay, so the first criteria for topological space is satisfied. The second criteria is satisfied. Let's take the third criteria. So let's take the intersection, okay, of any two sets. So let's take the intersection of any two sets. So let's take, for example, 1, 2. 1, 2, and let's say 1.5, 3.5. If I take the intersection of these two sets, and so the intersection of these two sets will be 1.5, 2, and this also belongs to T. Okay. Now I could now the third rule that we had, okay, for what defines a topological space is that the intersection that you take must only be of a finite number of sets, okay, finite number of subsets of open sets rather, okay, these UIs. Okay, now what would happen? Okay, so even though this is not part of our definition of a topological space, you could ask what would happen if I allowed myself to take an infinite number of open sets and then take their intersection. Okay, if I took an infinite number of open sets and took their intersection, would that belong to T? Okay, and you can see that suppose I have an infinite number of open sets, so I could take, let's say, for example, 1, 2, okay, and how do I do this? Yeah, okay, so let me explain pictorially. Okay, it's easier to explain pictorially. So imagine, so let's take the real line, okay, and let's take points between, let's say, 0 and 1. Okay, this is an open interval. Okay, and now let's imagine that we're taking open intervals, okay, and we're taking open intervals such that we take open intervals, and we go on taking open intervals in such a way that they are always, let's say, to the left of 0.5. Okay, and we take open intervals to the right of 0.5. Okay, and we take an infinite number of these. Okay, and we take an infinite number here. Okay, so we go on taking these open intervals and we go on taking the intersections of all these open intervals. Okay, what would be left? And we also take the intersection with 0, 1 itself. What would be left over after taking an infinite number of intersections?
So 0.5.
Yeah, just a single point, 0.5, right? Because 0.5. Oh, sorry. Wait a yeah, right. So if these are disconnected intervals, right, then they have no overlap. Okay. Oh, sorry. I made a mistake. Oh, what I really wanted to do is take another interval, let's say between 0.25 and 0.75. So I go on halving this thing, and then I half it again. Okay. So this is, let me just draw them in different color. So this, okay, and I go on squeezing the walls, okay, and I take the intersection of the set of all these sets. The only thing that is common to all these sets, okay, in the infinite intersection limit is just the single point, 0.5. Okay, it's just a single point, okay, which is 0.5. So now this point is a discrete point, and as we've discussed, this discrete point is like a closed set and it doesn't belong to this topology T. Okay, so if in our axioms we had relaxed the condition, or in condition C, we had allowed for infinite subcollections, okay, then we would have to include closed sets also. Okay, we would have to include closed sets inside T, or even half closed, half open sets, and therefore T would just become the discrete topology. Okay, and that's why you see that this topology, the usual topology, is different from the discrete topology. In the discrete topology, I also include each point by itself also, in addition to closed intervals, okay, on the real line. So this topology, where I only take open sets and their unions, gives me something more interesting than just the discrete topology. Okay, and it's allowed by the fact that my definition of what is a topology, for the intersection criteria, we allow any finite subcollection of I. Okay. Is this clear? This example? This particular example? Yeah. there's a question. Sorry, I can't see the names. Yeah, Utkarsh.
Yeah, so if we take a union of an open interval 1, 2 and open interval 2, 3, what will it correspond to in T?
So this 1, 2, 2, 3.
Yeah.
So these are two open intervals.
Yeah.
Right? And T has all open intervals and their unions. So T includes this.
Okay. So we don't need to define like something like an complementary intersection that's like removing the two element itself from this interval.
You don't need to do that. I mean, this is already included in T because we've demanded that the unions of these open sets are also part of T.
Okay. Okay.
Okay, so this usual topology is kind of interesting. It seems like a very mathematically abstract thing, okay, but we'll see that this gives us some very interesting notions, okay, of topological spaces, okay. Yeah, so this is what I was saying. So if we allowed infinite intersections in condition C, okay, or if we demanded rather infinite intersections in condition C, that it should be that those infinite intersections should also belong to T, then you would be forced to include closed sets or discrete points, and your usual topology would just become the discrete topology, which is less interesting. Okay, so the usual topology has some structure to it, which is not just either the trivial topology or the full discrete topology, but really it satisfies some conditions of this topological space by itself. Okay. Okay, so now let's do some more definitions, okay, from this. So now let's again go back to our abstraction. Okay, so not necessarily. So even though mostly we'll be interested in just the usual topology on Rn, okay, let's just be more abstract for the moment and go back to this general idea of a topological space. Okay, so let Xt be any topological space, that is, T gives a topology to the set X, and let A be some subset of X. Okay, so X is your original space, okay, and we took some subsets on it, T, which gave it a topology. But now let's take some subset of X, which is A. Okay, some subcollection of these elements of X. Then the original topology on X, okay, also gives rise to a topology on A. Okay, so even the subset of A inherits a topology from T. And how do we see that? Well, so if we take the original T, which is subsets Ui of X, this induces a relative topology on A, and to get this topology T prime, which is a topology on A, I have to just take the subsets of X and take their intersection with A, okay, for all Ui which belong to T. Okay, so I won't prove that this is a topological space, but it's kind of intuitively easy to understand why this would be a topological space, right? You're taking all those subsets, but you're only keeping the part that belongs to A. Okay, and you're taking all the UIs that belong to the original T, and you're keeping them inside T prime, but you're only keeping the parts that are inside A. Okay, and that induces a topology on A. Okay, so you either say that this is an induced topology or a relative topology. Okay, so let's do an example. Okay, so supposing we take X to be Rn plus 1. Okay, and let's take the usual topology on Rn plus 1. And let's take a subset A, which is an n sphere embedded in X. Okay, so for example, if you have three-dimensional space, I'm embedding a two-dimensional sphere, okay, in this three-dimensional space. Okay, so I draw it like this to indicate that it's the surface of a sphere. Okay, so the generalization of this is an n sphere embedded in n plus 1 dimensions. Okay, and the way to think about this is just think about the equation for the sphere. So in my n-dimensional space, I have x1 square plus x2 square. Sorry, in my n plus 1 dimensional space, I take only those points which satisfy this equation, x1 square plus x2 square plus dot 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 plus xn plus 1 square is some r square. Okay, that will give me a generalization of this. So for 3 dimensions, this gives me a 2 sphere. Okay, this is the equation of a 2-dimensional sphere. Okay, just like in 2 dimensions, I can embed a 1 sphere, which is a circle. Okay, it's called an S1. Okay, an n-dimensional sphere is called Sn. Okay, so an S1 can be embedded inside a 2-dimensional R2. Inside R3, I can embed this a 2-dimensional sphere. Okay. Okay, so now the claim is that A inherits a topological structure from X. Okay, A inherits a topological structure from X. Okay. So this usual topology gets transferred in some way to this from R3 to this S2. Okay. Okay, now let's define this idea of what are called continuous maps. Okay, so let X and Y denote 2 different topological spaces. So X and Y have their own topology. So let's say this is coming from some topology T, this is coming from some T prime. Okay, and there are 2 different topological spaces. So X and Y are the spaces which get a topology through some T and T prime. Now what we can do is we can define a map. Okay, this map is a map from X to Y. So if I have 2 topological spaces, we can take a map from X to Y. And we now give a definition of what it means for this map to be continuous. Okay, so the map is continuous if the inverse image, that is, if I have some X, okay, and the elements of X map to something in Y, and they may not map to all of Y. It may not be an onto map. Okay, so they may cover only some region of Y. Okay, and if the inverse image, that is, if I take this region of Y and then I invert it to find what region of X I'm looking at. So if this is F, okay, then I can find the inverse image. Okay, so that gives me. Oh, sorry. Okay. Now, okay, so now let's suppose that I cover some region of Y. Okay. Now within this region of Y, we look at an open set. Okay, that is one of the UIs that belong to T prime. Okay, we will look at one of the UIs that belong to T prime within this open set. Okay, and if the inverse image of this open set, that is, I find the points in X that through this map take me to that region UI inside Y. Okay, so I find this is the inverse image. So I'll write it schematically is F inverse of UI. Okay, is this region. Okay, so this is F inverse, and it takes me from this region UI back to this F inverse UI. And if the inverse of this open set in UI is an open set UI in X, so let me call this UI prime, let me call this UI. So T contains subsets UI of X, T prime contains subsets UI prime of Y. Okay. Then if I start with some open set UI prime inside Y, take the inverse image under F, and that gives me an open set in X, then we say that this map is continuous. Okay, so if the inverse image of an open set in Y is also an open set in X, okay, then we say that the map is continuous. Okay, now this definition of continuous may be different from the definition of continuous that we've seen with real numbers, as we'll see that these definitions also are the same. Okay, of continuous maps, so let's say between the real line to the real line. Okay, so topology gives you another way of defining continuity. Okay, so let's do this example. So let's take X to be real numbers, okay, with the usual topology. Let's take Y to be real numbers with the usual topology. Okay, and this is what you would think of as a discontinuous function, okay, from X to Y. Let's see that under this definition of what we mean by continuous map from X to Y, that this is also discontinuous. Okay, so what we mean by usual topology. So usual topology is we can take open intervals on X. Okay, this is one UI, right? This belongs to the usual topology T of X. Okay, and then I can also take an open interval on Y. Okay, so let me take this. Okay, so let me take this open interval. Let me take the points. So let me take the inverse image of this. So this is ui prime, okay, which is some subset of y, okay, or something that belongs to t prime in y. This is an open set. Okay, let me take the inverse image of it that would correspond to this region in X. Okay, and you can see that this is also an open set which belongs to the topology of X. Okay, but now there's a second possibility. I could have taken in Y, I could have taken this open set. Okay, and this is also a valid open set in Y. And now I could yeah, so now let me take the inverse image of this. Okay, and sorry, so I'm defining it so that at X is equal to 0, this is the value of F. Okay, so if I take the inverse image of this, okay, what it's going to give me is these points here will have an inverse image which is left close, right open, and these points here will give me something which is right open, sorry, left open also. And the inverse image is an open. Sorry, this place doesn't have an inverse image defined, so I can't quite do this. Let me just backtrack for a second. So we want to find, so the vertical axis is the space Y, okay, and we want to find open sets in Y. And open sets in Y that have an inverse image in X. Yeah, so let's suppose we take this point and this point. So this defines ui prime. We want to find the inverse image of this. The problem is if I take an open interval here, this point doesn't get included. But if I extend beyond that point, then these points have no inverse image.
So that would make the inverse image like half open, right? Like closed on one side, open on the other of the open interval taken around that point.
Yeah, I think so. Okay. Yeah, so suppose I take this open interval. The inverse image will just include this discrete point, right? And it will be left close, right open, here, like that. Yeah, thanks. Okay, so I think basically, yes, you're right. So if I include these points which have no inverse, okay, then the inverse image doesn't include any inverse for these, but it would stop here. So the inverse would be this left close over here, okay, which is this is x is equal to 0, which gives me this value on y. Okay, so the inverse image of this set ui prime, okay, gives me a left close right open set, and this is not a member of the ui, which are does not belong to ui, which belong to t. Okay, and therefore this is not a continuous map by the definition of topology, and therefore it's I mean, so either by topology or by functional analysis, okay, you would call this not a continuous map. Okay, so the definitions that we have for continuity between maps between topological spaces are really the same, okay, intuitively for the maps that you'd have between, let's say, real numbers, okay, or functions between real numbers. So let me give you another example. So let's take x is equal to real numbers and y is equal to x square, okay, to be the parabola. So now if I take an open interval on y like this, okay, so this is an open interval. The inverse image is the union of these two open sets, okay, which again belongs to ui. Okay, so this is ui prime. This is the union of these two is some ui, and that does belong to the usual topology of real numbers. Okay, so in this case, you can see that this is a continuous map. Okay, and so a continuous function is what you would think of as a continuous map. Okay. Okay, now let's do. Okay, so let me just define one last thing and then we'll stop. Okay, so let me define the idea of neighborhoods. Okay, in a topological space. Okay, and so suppose T gives a topology to X. So there is an X and then there's a T that gives it a topology. Then we define this idea of neighborhoods. Okay, so we take a point X belonging to X, and we define the neighborhood to be such that n is a subset of X. Okay, so there's a point X, n is a subset of X. Okay, so we have some point X, small x. Okay, and n, the point is that this n has to contain some ui, some open set ui, at least one, which contains x. Okay, and then you define n as a neighborhood, okay, of the point x. So this n is a neighborhood of a specific point x. So this neighborhood need not be open. Okay, that's the important point about the neighborhood. The neighborhood need not be an open set. For example, on real numbers, 1, 2 is a neighborhood of 1.5. Okay, you can define it because it contains the open set 1, 2, which so n is this, but n contains 1, 2, and 1, 2 contains the point 1.5. Okay, which is x. So this can be a neighborhood. Okay, closed sets, half closed sets, these can all be neighborhoods of a point x. Okay, so n need not be open. Okay, and if n is open, then n is called an open neighborhood, but it doesn't have to be open. Okay, so yeah, so as I've already given you example, so if you take any x belonging to -1, 1, then the closed interval -1, 1 is a neighborhood of x. Okay, so this is the last definition I'll give you for today, and then we'll stop. Okay, so the last thing I'll talk about is the idea of what is called a Hausdorf space. So you consider topological space X and T, and this space is said to be Hausdorf. Okay, that's just a name given to it. If you have for a distinct pair x and x prime, so if you take any two x and x prime belonging to x, and there always exists a neighborhood nx of this x and a neighborhood nx prime of this x prime, such that the intersection of nx and nx prime is a null set. Okay. Now, for real numbers, you can see that this will always be true, right? So real numbers with the usual topology. Okay, if I take any two numbers, I can always construct neighborhoods that do not intersect. Okay, and you can always, so real numbers with the usual topology are a Hausdorf space. Okay, so there are sort of weird examples that you can construct. I'll just leave you with this one. So if you take X as A, B, C, D, and the set U's, okay, U is the null set, the set X itself, and then these two subsets, the set which includes only A and the set which includes AB. And the first thing is to show that this collection of U0, U1, U2, U3 together with X forms a topological space. Okay, so you can check this as a homework exercise, check this. Okay, but at the same time, XT is not Hausdorf. Okay, because it's possible to find a neighborhood of some member of X, okay, such that so if I take an x1 belonging to X and an x2 belonging to X, it's possible to find a neighborhood of x1 that is, it's not possible to find a neighborhood of x1 that does not intersect a neighborhood of x2. Okay, so for example, supposing I take x1 is equal to C and x2 is A. Okay, so I take, this is x1, this is x2. Okay, then let me construct one neighborhood. Okay, so N1 is equal to U3. So the only valid neighborhood of x1 has to include C in it. So the only valid neighborhood is this one, okay, which is U3 or yeah, so it has to include U3 at least. Okay, so therefore it is U3. So this is U3 is the only valid neighborhood of the point C, okay, or x1. Now what that means is if I take x2 and I take any neighborhood of x2, that neighborhood, okay, will be either U1 or U2, okay, or U3, and the intersection of U1 or U2 or U3 with U3 is non-zero. Okay, so it's not an empty set, and therefore, okay, this set, this X with this topology is not Hausdorf. Okay, but for almost any example that we will actually be interested in, the spaces that we look at will all be Hausdorf. Okay, so as we discussed already, Rn with the usual topology is Hausdorf. Okay, okay, so we'll stop here and we'll resume tomorrow. We just have to decide the time for tomorrow's extra class. So some students said that 11 a.m. tomorrow is not possible for them. So they, yeah.
You mean on Saturday, right? Not tomorrow?
Sorry, not tomorrow, Saturday. Yes, Saturday. So some students said 11 a.m. is not possible. So one alternative time is 3 p.m. Does anyone have a conflict at 3 p.m. on Saturday? Yeah, go ahead.
So one of my courses is on 2 to 4 from Saturday, on Saturday.
2 to 4. How many people have a conflict with Saturday's class? At 11 a.m.? Yeah, just put your hands up so I can just see. Okay. What time is your conflict, Prakhar? Prakhar, what time is the conflict? Like you said, there's a tutorial and something else after that.
Yes, sir. So we have to take a tutorial from 11 to 12.
11 to 12. Okay. Okay. How about 4 to 5:30?
Sir, actually.
Yes. Go ahead.
Yes, sir. So I was just saying that actually Devashish and Shashwat also have the tutorial and they are not currently in the meet point.
Okay.
I'm here.
Yeah, so 4 to 5:30 works. Oh, sorry.
Okay. Does anyone have a conflict with 4 to 5:30? Okay, so let's meet at 4 p.m. on Saturday. Okay. So Malvika, I mean, it's right after your previous class, but hopefully it'll be okay.
Yes, sir.
Okay, and of course, as usual, we'll record the lectures, but it's better if you come to class and ask your questions. Yeah, so I apologize if it's going to seem very mathematical for the next few weeks, but hopefully the basic idea will become clear, and it's good to be rigorous because instead of hand waving about what we mean by curved space and curved space time and so on. So once we lay down everything rigorously, it'll be much easier to see what exactly, I mean, rigorously defined, not rigorously proved. Okay, we won't necessarily prove all the theorems, but at least we'll define what we mean, right? And then that will help us talk about curved spacetimes much more easily. Okay, so we can stop here. If you have any questions, I'll stick around.